Good morning, folks. Welcome to our March EMX, the end of winter, we hope, in the Northern Hemisphere at least. And we've, of course, got another really exciting program here today. And one case using carbon nanotubes as test tubes, nano test tubes. And then, of course, David, who is has a long pedigree of this electron microscopy in the electron microscopy field. So good morning. We'll have today's session, and then the next one will be on May the 6th. And I will hand the baton over to Professor Hua Chu, who will introduce our biological speaker. Thank you.
Hi, good morning. It's my great honor to introduce you David DeRosier, our speaker this morning. David is a long-term colleague of mine, and I personally get lots of benefit in talking to David every time. And David pioneered the work in three-dimensional reconstruction for electron microscopy in biological samples. He laid down the most fundamental algorithms and mathematics, how one can reconstruct the three-dimensional structure from a two-dimensional projection maps. So David's work is definitely pivotal for all the cryo-EM structure that we have been able to do today. And we really in-depth to David's insightful and pioneering work some years ago with Alan Cook at the Medical Research Council in Cambridge. And with his continual effort in pushing the envelope in electron microscopy and cryo-EM, David always raised insightful questions and tackle extremely difficult problems. And he is a professor emeritus from Brandeis University, but he continued thinking about these very difficult problems. And we always look up to David for answers for difficult problems. And for his contribution, he has been recognized by many professional society and academies, including the National Academy of Sciences in USA. And this morning, we are delighted to hear what he has been up to recently. And he raised a very provocative title in his talk. He asked the question, where is my protein in the cell? So David, let's tell us where you find your proteins.
Okay. I'll just share my screen. Oh, I don't see it up here. Hold on a moment. My apologies. It was just there.
Yeah, it was okay. It was there a while ago.
It was?
Yeah.
Oh.
You
So
just,
you can see it?
yeah, we can see it, right.
Okay. Who knows? It
This
must
looks
be
like-
user-friendly, because my view has always been that user-friendly things never work properly.
This looks like the last slide, David.
Oh, yes. Let me just back up through them quickly and then try to, there we go. Okay. Thank you. Sorry for that. So many people have laboratories that have beautiful backdrops. I've seen ones in Switzerland where you have a beautiful view of the mountains with snow. Well, I'm retired, or re-retired, as I'll tell you. And this is the compound in which I live. So this is my daily background. So the title of my talk is, where in the cell is my protein? And it really is about visual proteomics. Now, things really began in 1995 when the Baumeister lab introduced cryo-electron tomography. And I must say this was a bit of a startler because people had worried so much about radiation damage taking a single image. The idea you could take a whole tilt series and reconstruct something that wasn't scorched was really quite a remarkable. And this was Wolfgang Baumeister and his group, their proof of concept. They went on to make many developments in the field of cryo-electron tomography, so we're very grateful to them. But initially, this field was limited to thin samples, such as lamellipodia or small bacteria. Now, my interest in locating proteins began in 2000. And I had seen people labeling structures with small gold particles, nanogold particles, and I thought what we needed was a clonable tag where you could grow an EM visible gold particle, and the idea from a gold salt. And the reason was that you would get much more efficient labeling because you would grow the particle there, and there wouldn't be the issue of steric interference because growing a particle could generate more energy than and pushing aside anything that was blocking it. So a very good graduate student, Chris Mercogliano, and I showed that metallothionein, which is a 60 residue protein, 6 kilodaltons, really tiny, can bind as many as 40 gold atoms and is visible in the EM. Chris went on, and I retired, but Wanzhong He and his group extended this work by modifying metallothionein and the recipe for labeling cells. Now, he did this in fixed section cells. And here's an example of oligosaccharyl transferase, which is a membrane protein found in the ER, in nuclear membranes. And each dot there is one molecule of OST with metallothionein, and he also put on GFP so he could see that the labeling, that the protein was expressed properly. But you can see the degree of labeling is quite heavy, and the background is only a couple of percent. There are a few dots around there, a few percent. This was not really picked up by people in live cells except by Christina Risco, because gold compounds are toxic to cells. In fact, metallothionein is one of the ways that cells have of protecting themselves from gold compounds. So it really hasn't found much use in living cells. In 2005, I retired to become a postdoc in the DeRosier lab. And the idea there was to localize proteins in cryo-electron tomograms or micrographs using single molecule localization microscopy. I won't tell you how I thought it might be done, but within a year or so, FPOM Stormstead came onto the scene. And so we picked up from there. And a postdoc in the DeRosier lab, Mark Nemani, and I built a cryogenic FPOM microscope with a 1.2 objective. And here's the objective lens, and here's water. Now it's flowing water because otherwise the water would freeze. So you have to flow it past. And then there's a cover slip, and then there's a cryoliquid. This is a liquid that is liquid at minus 140 and doesn't boil until quite a high temperature. So it remains liquid over a large range. And then you have a cryo block and of course cold nitrogen gas to cool it. And the EM grid sits right here at this junction. And with this, we were able to achieve double labeling, 2 labels, eutrophin with PAGFP and vimentin labeled with PSM orange, both of which switch. PAGFP turns on and PSM orange switches from orange to red. And here's an example of a whole, this is not one, this is many, many little dots that we have just shown to show that eutrophin and vimentin are separated as they should be. And of course, you can see 200 nanometers here. So you can see this really is super resolution. And our resolution in the cold was a little bit better, about 35 nanometers compared to a sample run at room temperature. It's about 45. This was originally an effort to try and identify the location of fluorescently labeled proteins that then could be mapped onto a micrograph of a lamella or a tomogram. Now in 2006, Mike Marco relieved this idea that you needed only thin lamellipodia from cells by showing that you could use focused ion beam milling and a cryo sample without disturbing the vitreous nature of the ice. So this was quite a breakthrough. And the Jürgen Plitzko and Wolfgang Baumeister and the collaborators like Elizabeth Villa went on to improve this method and make it now one of the premier parts of structural cell biology. That is, focused ion beam milling to produce a lamella of a cell. And here is the lamella on an EM grid, which you can put in the microscope and tilt and collect 3-dimensional data. So this is now, I think, the cutting edge of structural cell biology. So for the rest of our discussion, we'll assume we have some kind of lamella. Here's one from the work of Joe Poliano, Elizabeth Villa, and David Agard. It's a giant phage-infected cell. And you can see here, you can see ribosomes, you can see phage, maybe phage parts over here. But there are lots of other things. There are lots of proteins you're interested in that you don't know where they are. So besides tags, that is putting on a gold particle or a fluorescent label, what are other possibilities for locating structures of interest? Well, again, the Baumeister lab introduced template matching to identify and locate protein complexes in a tomogram. So he used 3 structures, thermosome, GROEL, and the proteasome. And here he didn't have a cell, but rather a liquid that was with a mixture of thermosome and proteasome that were frozen in a thin layer on a grid. And then he took, made a tomogram of it, and then looked at the cross-correlation coefficient with particles in the image. So if the sample contained the 20S proteasome, then the 20S template did a much better job. You got a higher cross-correlation coefficient with the correct structure than you did if you used the incorrect template. And the same is true for the thermosome. If you use the correct template, this one, you would then get a higher cross-correlation coefficient. So he showed you could pick out and differentiate different kinds of particles, even though in some sense they look very similar. So this was a proof of concept. this has been picked up by others, and here is an example by Bronwyn Lucas, who I think spoke here a while back, along with Nigro Grigoriev and their collaborators, and used to detect and differentiate incomplete from complete ribosomes. So the incomplete ones, of course, will be in the nucleus, and the complete ones will be out here. So if you use a template from the incomplete ribosome and you do template matching here and here, you see the template, the peak that you get in the match is very low if you're using an incomplete template in a region that has complete ribosomes. Whereas if you look at the matching of this to the particles inside, you get a much higher peak. Conversely, if you use a mature 60S particle, you get a much better match in the cytoplasm, this peak here, than you do in the nucleus, slower peak. So they were able to differentiate ribosomes. So what is the smallest protein? By the way, they use micrographs, not tomograms. Excuse me. So they could use small templates as parts of ribosome to explore what the sensitivity is of looking at a cryomicrograph and extrapolating it down, and they arrive at a value of about 300 kilodaltons. This is not from a tomogram, but from a micrograph of a lamella. Now, another group used tomograms instead of untilted micrographs, and they were able to locate tubulin dimers reliably. And so this is their template, this little box here, it's a tubulin dimer. And what you can see in this Z-score map, which is sort of the how many standard deviations you are above noise, you can see they get quite good recognition. So here's a structure that is about 100 kilodaltons if you work using their algorithms, you can pick up something smaller. Now, if you can pick out a structure, you can also think about doing some averaging. And of course, this was not surprisingly introduced by the Baumeister lab once again. And here is a suspension of thermosomes, and he made a tomographic series of this, not a cell, but a slurry suspension of thermosomes. And then he cut out three-dimensional particles from the tomogram and aligned them and averaged them. And here are two different methods of doing the averaging. And here's sort of like a Fourier shell coefficient. And this was, of course, a proof of concept to show that subtomogram averaging was something that could be done and you could recover a structure. So it's very important. Well, Chen et al. In the Agard lab milled lamellae of an intact mammalian sperm. So this is not an isolated eukaryotic flagellum, but lamella cut through it. And using subtomogram averaging, they were able to produce a 6 angstrom map. I don't know if this is blocking it. All these little user-friendly things get in the way. Anyway, so what they did was they carved out the parts of the structure that were unassigned densities, and then they used predicted models from the slightly over 21,000 proteins in the mouse genome using AlphaFold 2 to match up the predicted folds with the isolated densities from their subtomogram averaging, and they were able to fit them. This is really quite remarkable. So if we have a structure made of many components, we can use subtomogram averaging to identify them and produce atomic models. And of course, in this case, the molecular weight of the component is not as much an issue. So this is a recent paper. It's really quite amazing what can be done. Now, what is the bottom line for using template matching? So here's work from Dickerson and Chris Russo's group at the MRC. And this is from one of their papers. This is the current technology, 300 keV plus an energy filter. And here's the line, and this across the bottom is the specimen thickness. So of course, the thicker the specimen, the harder it is to find a structure simply because you have background. But you can see in the region of about 1,500 thick or 150 nanometer lamella, you can identify something that's around 100 kilodaltons. It's exactly what the group in the previous slide had done. Now, if you use chromatic correction and 5,000 angstroms of defocus, you can do a bit better. And this decides if you need 4 angstroms to identify your structure, you get this curve. If you can do so with 9 angstrom resolution, you can do a bit better because you don't need the high resolution data. Now, if you add chromatic correction for the chromaticity of the beam, meaning that you have fewer electrons that don't have the correct energy, you can, of course, do better. And this is, of course, the line is about the best you could do with the CC correction, phase plate, and so on. Now, the final chance for improving the minimum recognizable mass is here if you use liquid helium, because you get a reduced radiation damage, and you can see you could get to somewhere around 28 kilodaltons. So that sort of represents a kind of ultimate bottom line if you have a CC corrected microscope with a laser phase plate and liquid helium capabilities. I'm trying to imagine the price tag on that. It would probably be pretty large. Now, so what happens if your protein, at least in today, is less than 100 kilodaltons? Well, one possibility is to use fluorescent tags, as I had thought to do at one point. They're easy-ish to generate. They're slowish to collect data. And I put slowish because some people are faster than others, but even so, it's might be an hour. And the other thing that really is the killer, it's difficult to impossible to map those coordinates from the light microscope onto a tomogram or a micrograph. There are all sorts of issues in doing that. Of course, my favorite was a clonable heavy metal tag. Excuse me. That you could detect directly the tomogram or micrograph. And the problem is that you want to get the gold into a cell that's in a happy living state. It's not so clear that has been done. Christina Risco has suggested that you could get the labeling done in a few minutes, and that the cells don't appear to be damaged. But I think this hasn't really been picked up. So the final is to have clonable detectable tag that you can detect using a target structure. And so these could be detected directly in the tomogram or micrograph. And of course, they have to be in present days over 100 kilodaltons. And one of the Chan Zuckerberg initiatives has funded the development of such a tag. So we'll see how that does. And of course, the good thing about the gold is it's very small tag before you put gold in. And this is quite large, so it might interfere with some of the functioning. So there's still a lot of room here to figure out a better way to tag smaller proteins so we can locate them in a cell. These are the only three that come to mind. Now, FPOM microscopy is maybe not ideal for locating proteins in tomograms. What might it be good for? Well, people use correlated light and electron microscopy to identify cells on a grid that are suitable for milling, that is, cells that have expressed their label. If our target is everywhere in the cell, of course, you can mill a lamella anywhere and get the data you need. If it's not, you could potentially use fluorescent light microscopy to see if the fluorescent target was successfully captured in the lamella. And I saw an example of that recently from the laboratory of Elizabeth Villa. But better yet, could we use the fluorescent light microscope to identify where to mill a lamella within a selected cell? Well, we may need super resolution. And the reason is that with an ordinary 0.9 objective, you see you have this huge point spread function, which is much bigger than the lamella you want to mill. So you need super resolution because it reduces that point spread function and could successfully locate where to mill the lamella. As far as I know, this has not been tried, but it is a thought. Now, there are commercially available microscope. Here's the Thunder from Leica. And here is a milling machine with a fluorescent microscope built in. Now, these could potentially be adapted to super resolution. There's a problem, they're both upright. The problem with upright microscopes is that in a blotted grid, the top of the cell is a bump, and that bump is optically interferes with the rays emanating from the fluorescent protein, so you get a blurred image. If you could turn the sample over and look at the flat underside of the cell, you can avoid the curvy cell problem. But if you do, you have to remember that when you're looking, you have the fish tank effect looking through a flat side of a cell that has a refractive index close to water. And in fact, the distance you measure is not the distance you want. You have to correct it for the change in refractive index of the fish tank effect. And then the other thing to remember is that you measure the distance from your objective. That's not what you want. You want the distance from the grid so you could determine where to mill it. So you need a second fluorophore, and you could then measure those two positions and correct it by the change in the refractive index. So of the cell relative to air or vacuum. Anyway, it seems evident that we would like to have a super resolution like an FPOM microscope built into the FIB-SIM device, so we could determine where to mill each lamella if that were our only goal. If, however, we need to observe cells to capture a particular event prior to freezing, we may want a cryo-capable standalone fluorescent light microscope with super resolution capabilities, so we can map the XYZ positions at which to mill lamellae. And the second thing, and I've heard this at a recent meeting I was at, people would like a freeze now button, so that when you see a particular event, you push a button and it freezes the cell where you are. Now, this doesn't exist. The question is, can you somehow get a blot and freeze capability engineered into a stage on a standard light microscope? Seems kind of crowded. But here's a recent development in microscope objectives to think about. One I thought was very interesting and offers some potential. And this is to use a Schmidt or mirror microscope objective. And this is from this group here by Voigt, who is the lead author. And I want to show you some features of this. Here's the mirror here, and here's a cell. The first thing you want to know is over here. The numerical aperture is quite high, about 0.7 to 0.9, depending on the medium that's in the region of the sample. The second thing is the field of view is huge. It's a better part of a millimeter. And the final thing that really got me excited was the working distance is 11 millimeters. It's not 11 microns, it's 11 millimeters. So there's a lot of room in which you could think about putting in some kind of apparatus to blot and some jets to freeze or something. So, you know, this is something to think about. So here are the challenges for visual proteomics. The first is develop visible tags for low molecular weight structures. Once you can, where you need for template matching. The second is to develop a FIB-SEM machine with an inverted super resolution light microscope. And the third is to develop a super resolution freestanding microscope with a freeze now button and lamellar locating provision. Now, the thing about these latter two things is it's one thing to have some lab with a lot of talent to build one, but what we really want is to have these things made commercially so they're available to everyone. So there's a real challenge in terms of getting one, showing that there's sufficient interest in such a device, and then maybe facilities, they're going to be expensive, I presume. Facilities like the ones at Stanford would be able to run such an operation so everyone could have access to it. I don't know the answer. I don't know if there's time. I know I'm about 5 minutes into the question. Let me say a couple of words. Yeah.
Go ahead, please.
Okay. So the one thing about tomograms is the missing wedge. And there are methods of dealing with a missing wedge, such as nonlinear filters or artificial intelligence-aided filtering. Those have been used. And here's an example of a filter, a nonlinear filter, used by Sadat and co-workers to try and restore the missing wedge. And what you can see here is this has done a pretty good job, this filter, of making the elements on this microtubule visible. You can see the dots. So the filter has made some of the features on the map more interpretable, but we don't know that the Fourier values in the missing wedge are approximated by those that would be determined from a plus minus 90 degree tilt series. So it can improve things, make them more interpretable, but you don't really know if you're filling in the missing wedge for the following reason. Without any constraints, such as enforcing the lamella thickness, Fourier coefficients could be any size and any phase. And filling in the missing wedge is not sufficient because any filter with, for example, a multiplicative factor, whether correct or incorrect, will fill in the missing wedge. And to show you why that's true, consider enforcing the lamella thickness. So here we're going to enforce lamella thickness with this operator that is 0 here and 1 here. And this is the dimension of the missing wedge. And here is the Fourier data from the tilt series as the series of fans. So this is the Fourier transform of the 0-degree tilt, the 15-degree tilt, and so on. This is the Fourier transform of this, which is a sinc function. And when you multiply these two together to enforce the thickness of the lamella, in Fourier space, you convolute these. That means you put this Fourier transform, which is a function of z only, down at every point in this transform. And of course, with the weight of the Fourier value there. And of course, what you do is you put it down here at 0, a little here, a little here. And of course, you can see you fill in the missing wedge. But you don't know that you filled it in with correct values. That you enforce the lamella, but whether those additions move you closer to the correct amplitude and phase in the missing wedge, you don't know that because you don't know how important a component that is of the values that would be in the missing wedge if you knew what the missing wedge contained. So my approach is try to do something that's linear, where you do understand what you do. And this is my first simple example. Here is the data you have collected from the tilt series at a particular reciprocal radius. And this is the angle of the tilt. And we're going to say that it can be derived from a series of essentially periodic functions, these e to the I and phi, and some complex amplitude that weights it. So what we're going to do is to have this as the data, and these are the unknowns, and these terms form a matrix that operates on these terms to generate those. So what we want to do is to invert the set of equations. And when we've determined the g's, we can then compute the Fourier coefficients in the missing wedge using this formula. Once we've determined g's, of course, the point is that the eigenvalues of this matrix, these terms here, tell you whether the errors are being reduced or amplified. So the errors in the data by the inverse average of the average of the inverse eigenfunctions gives you the propagation into the answer. But that alone is not sufficient. What you want to know is where do those errors show up? So here is an example of phase errors. This is 0. This is 90 degrees. And these are phase errors with differing signal to noise ratios, even when the average value of 1 over lambda is favorable. And here's the error in amplitudes. And so if you look at this, you can say, well, that's not too bad. If I'm in the right quadrant, that's as good as most telescope manufacturers do when they're grinding mirrors or lenses. But this is not one value. This is an average. So if the average is, let's say, 80 degrees, it means there's many with phase errors below 80 as there are above 80. So in fact, these errors are really horrendous. And this is the region of the missing wedge. And you can see the value before you get to the missing wedge, which is 60 to 120, they're quite low. So all of the errors are being piled up in the missing wedge, because of course those errors don't show up in the original data. So the answer is it sweeps all the dirt under the carpet. So the only way to improve this, in my view, is to in fact go into real space where you can enforce things such as the thickness of the lamella. Anyway, I leave you with a view of where I will spend my afternoon today and ask if you have questions. Thank you.
Thank you very much, David, for this very thoughtful questions you raised about cryo-electron tomography, and particularly in the cellular systems. We have a couple minutes for questions, and for those audience who like to ask questions, please type your question to Q&A in your Zoom. And the first question, David, is that does the use of two photophores to correct for the fish eye effect not overlapping the information content?
I'm not quite sure I understand. Maybe yeah, go ahead, Bob.
Yeah, so you can open a Q&A button, and the question is about if you have two chorophores to correct the effect, would those overlap the other information in the cell?
Oh, I see. And no, because you can focus up and down. So I think you can separate them in Z. I'm not sure that that is the right answer, the answer to the question this person asks.
Okay.
The next question, I can read it. How to blot the sample when we find the better event using LM super resolution? Well, of course, I absolutely agree. I don't know how to do that either. But I think the point about that Schmidt objective is that it gives you a lot of room. You have a centimeter of room as opposed to, you know, a fraction of a millimeter. So, so I think it's a question of engineering that someone needs to build and develop one to see if it works. And then from Eva Nogales, hi Eva, when do you think 2D versus 3D template matching would work better or worse? When do you? 3D template matching seems to do better, according to that one paper. But they used different ways of doing the matching. So it's not clear to me what part of the increase from 300 to 100 kilodaltons might be due to the algorithms they use and what is due to doing it in 3D. But you would expect that if you have 3D data, you would be better able to do the matching, provided that things like sample damage weren't an issue. So I don't know if that's completely answered your question. Can symmetry, from Mike Schmidt, can symmetry help for ID of particles as a signal in itself, over and above just making the total molecular weight larger? Yeah, I think symmetry will. And the reason it does is because it concentrates the diffraction data into spikes. And those may be easier to pick up when you're doing cross correlation, if you're working in reciprocal space. So having a symmetric particle may help quite a bit. One last question. One major hurdle in cryo super resolution imaging is devitrification due to laser dose. Would you like to hear your thoughts on this? Yeah, absolutely. And you really want to stay away from devitrification. And the dose that your specimen can tolerate, that is the power from the laser that is dumped in the specimen, depends on the kind of grid you have it on. So it seems that there's room for using different kinds of grids to reduce this, and it's definitely something to worry about if you're doing any kind of fluorescence microscopy on frozen samples. You really want to determine what power the maximum power you can use without devitrifying your specimen. So it's really important to check that.
Okay, good. Thank you very much, David, for answering all these questions. All right, I would turn the floor back to Bob to introduce our next speaker.
Okay.
David, could you unshare your screen, David? Thank you.
Thank you very much, David, for a brilliant talk, and wow, for the kind introductions and hosting. I'm very pleased to move on to the physical sciences talk and introduce Professor Andrei Khlobystov, who's originally from Russia and has immigrated to the United Kingdom, currently at the University of Nottingham. He did a postdoc at Oxford University, and I met him at the Salve meeting in Germany last year, was very impressed by his work, and I'm looking forward very much to him showing how to use carbon nanotubes as test tubes for chemical reactions and to use to good effect the electron beam to assist them. So Andrei, looking forward very much to your talk, please.
Bob, thank you very much for a kind introduction. And thank you for inviting me to speak here. So it's a great honor to give a talk in front of this audience. And as Bob suggested, I will be talking about carbon nanotubes as containers for molecules. And the topic of the lecture will be on imaging molecules in action. So I will start with this quotation from the magazine Chemistry World. It's a magazine of the Royal Society of Chemistry, and they published this article a few years ago, Seeing is Believing, where they make the statement saying that chemists have devised many ways to illustrate how the molecules react using models, symbols, curly arrows. And it's easy to believe that this is reality of the chemical reactions. But the question is, of course, do we really know what happens at the atomic level when molecules react? What would we see if we could actually watch the molecules reacting in real time? So it's a big question. Of course, you already know that it's very difficult, impossible even, to do it using just visible light because of the diffraction limit. We can't really go down to molecular size here. So we need an alternative source of radiation, and that what electron beam allows us to do in transmission neutron microscopy. So you're probably familiar with this formula. It describes the relationship between the wavelength of the electron and the energy of the electron, and we can essentially accelerate electron to the desired energy. 80 kiloelectron volt, for example, is quite popular in TEM now, and reduce the wavelength of electron to really small length, smaller than the size of the atom, and then, of course, allows us to study molecules at the single molecule level. So this is one of my early pictures. This is the high-resolution TEM image. So it's a phase contrast image of this fullerene molecule, which contains a cluster of the 3 atoms of scandium inside. So you can see this triangle. And outside, it has a pyrrolidine organic group attached to the surface of the fullerene with a benzene ring on it. So you can see everything, what is inside of this fullerene cage and also what's on the surface. So this is great, but the other great thing, of course, is that we have lenses for electrons, so we can construct microscopes very effectively. The one thing we should not forget about electron is that there is a mass. this, of course, means that our very fast electrons in the microscope, they have kinetic energy, quite substantial momentum that can be transferred to the atom during the imaging of our molecules by electron beam. So that is what most of the microscopists call electron beam damage, and there are different mechanisms depending whether our electron beam interacts with an atomic nucleus or with a valence electron of the atom. Because we look at very thin object, so it's effectively a single molecule, which often is embedded in carbon nanotube, and that means very good thermal contact and very good electrical contact. We can really boil down all the interactions between the electron beam and molecule to this, what we call knock-on effect mechanisms, where the kinetic energy or momentum of the electron is transferred to the atom of the molecule. And if the energy is sufficient, we can break the bond. So other effects such as ionization, heating, or dissociative electron attachment mechanism can be largely ignored if we are dealing with a single molecule in a highly conducting matrix. So let's just take a look at this equation that describes the amount of energy transferred from the electron beam to the atom of the molecule. So the only thing we need to know is the mass of this atom, capital M, and energy of the electron beam, which we define by the imaging conditions of our microscope. And that's basically all what we need to know. And we can calculate maximum energy transferred from 80 keV electron beam to, for example, atom of platinum. And this is almost exactly 1 electron volt, which is good. I mean, this is something that we can cope with. This is not going to change behavior of the platinum atom that much. The other thing, of course, to say, I'm not talking about this in my talk, but what is important is the cross-section of the interaction of the electron beam with the atom. So, so if you take this into account, so this is not so bad for the metals, for example, this energy transferred to them. Where it becomes really bad is for hydrogen. Of course, it's 185 electron volt to hydrogen. This is well above energy that is required to break any chemical bond containing hydrogen. And this is clearly bad news for anything that is organic or biological. As far as the carbon is concerned, so at 80 keV it's 15.8 eV. So that depends where this carbon sits. You know, if it's carbon inside the carbon nanotube or graphene, that is not bad. So actually this is below the threshold required to knock out the carbon atom from graphene or carbon nanotube. But if you talk about carbon in the organic molecule, that is already enough to break the bond and start chemical reaction. So in essence, what we need to know about is the energy barrier or displacement threshold. It depends what terminology we would like to use, but chemical or electron microscopy terminology to break the bond. And when we exceed this threshold, the bond breaks and the chemical reaction starts. We can describe reactions in electron beam using chemical kinetics, or at least we can try to do so. So this is a simple reaction, A-B bond, which then becomes 2 separate atoms. And instead of the sort of traditional Arrhenius equation that we all used to use for thermally activated reactions, here we need to know about the flux of the electrons J, or dose rate of the electrons. So this is something that we control very easily by the brightness knob on the TEM. And sigma d is a constant which includes in itself all the information about the nature of the bond, the barrier for breaking the bond, energy of the electron beam, and the mass of the atom. So effectively, we can accelerate our reaction by increasing brightness during our imaging, or decelerate this reaction by spreading the beam. So this is a very convenient way to control chemistry. We call this method, well, just within our group really, chemical TEM, or ChemTEM for short. So let me tell you a little bit more about the test tubes, which are carbon nanotubes in our case. They are very useful for molecules. They interact with most molecules through very effective van der Waals force. Molecules stick to the surface of the nanotubes, and then at elevated temperature, they can diffuse into the nanotube interior and become trapped. And normally this process is irreversible. So once our molecule is inside of the carbon nanotube, it cannot come out. And we can safely take this nanotube, place it on the TEM grid, and insert it into the vacuum of the electron microscope without any fear that we will be losing molecules during our imaging experiment. Also, as I already said, nanotubes, carbon nanotubes have very high electrical and thermal conductivity, which means that we can also do in situ heating experiments in nanotubes or apply electrical bias and look at the electrochemical processes. So now we're going to zoom out from the world of molecules into the macroscopic world. And that just gives you appreciation how small things are at the molecular level. So this is all drawn to scale. It's 1 millimeter. Okay, so carbon nanotube, in fact, is in the Guinness Book of World Records as the world's tiniest test tube. So if you have an issue for 2005, you can find the record there. So we have our test tube. We have molecules in the test tube. We put it on the TEM grid, which then goes into the TEM. And you're probably already familiar with the layout of the TEM. So electron beam comes from the top. The sample is somewhere in the middle. Then have an objective lens, which collects electron beams below the sample, and then we form the image at the bottom, this column. So let me show you the first example, a very simple diatomic molecule. This is rhenium-2, so 2 rhenium atoms. Rhenium is a transition element from the bottom of the periodic table, very important in catalysis. And this is one of these atoms that really like forming intermetallic bonds, which are quite strong. So they've been studied for about 60 years, this kind of bonds, and the result of controversy. Is there a bond between the atoms, and is it strong? And what is the bond order? By bond order, I mean that the transition elements have 5 d orbitals, which means that the bond can be double, single, double, triple, quadruple, or pentuple. So you know, the bond order can be different, and this is a big question what that is. So here we have this pair of atoms which we created inside carbon nanotube, and because of the scattering of electron beam is very strong by rhenium, we can see them as 2 dark dots on the background of the nanotube. And also we can take the time series. So here we're observing this pair of atoms tumbling in a nanotube. Sometimes they're on top of each other, and then we have a darker dot. And as we're doing so, we can measure the bond length. So to our surprise, we found out that the bond length changes during this molecular acrobatics in the nanotube, and it switches between quadruple, double, and single. So that was interesting. So it's actually, probably adds more to the debate about the nature of the metal-metal bond. What perhaps more fun is actually to look at this pair of atoms over time and detect the moment of breaking the bond. So now you can see the bond is broken, now it's reformed, and in a second it will break again. So we know when the bond is broken between the atoms because they start behaving as 2 separate species. And also we know about the bond length really from calculations and from the atomic diameters of the rhenium, and that has allowed us to detect the moment of the exact moment of bond breaking. So what we observed is this very strange elongation of the atoms just before the bond breaks. And this is quite a strange thing. We don't quite know what that means really. We can only assume that this is something to do with the vibration, very high amplitude of vibration of the atoms when the bond is very long and stretched just before it breaks. And of course, it's a reversible process. The bond then reforms and we go back to the original rhenium dimer. The other type of nanocontainer, which is very helpful for confining molecules and bringing them into the TEM, is Buckminster fullerene. So it's 60 atoms of carbon forming this truncated icosahedron cage. We have, of course, it's 0.7 nanometer. That's the diameter, but we have to, of course, add the thickness of the molecular orbitals, the electron density, and that leaves about 0.4 nanometer void within the fullerene. So, which is just enough for small, medium-sized atoms to be squeezed into this cage. So there are different methods how to make this so-called endohedral fullerenes. So we can use something called molecular surgery, where we chemically open the hole in the fullerene and then put something inside, followed by stitching the fullerene again, chemically, of course. There is electric arc discharge, which is quite useful for putting metals into the fullerenes. Or there is something called ion beam implantation. That's the method that I'm showing here. So we have a crucible in a vacuum, which vaporizes fullerenes. And as they fly through the vacuum chamber, we fire, in this particular case, nitrogen atoms, ions. And collision, of course, can be quite strong, quite energetic, and this is not good because in many cases we simply smash the fullerene molecules into pieces. But about 1 in 10,000 collisions is successful, so that the atom that we're firing at the fullerene can become trapped inside. So fullerenes produced by this method, they are the second most expensive material in the world officially, and you could guess what's the first most expensive material in the world, and write in your comments. So here is an interesting example of krypton. So krypton, as you know, it's a noble gas. It has the size exactly right for the cavity of the fullerene. So this atom sits in the middle of the fullerene, so you have to imagine electron density on the fullerene as well. So the krypton is not levitating inside, it's just pushed to the center by the electron density of the carbon atoms. And in high-resolution TM images, krypton is quite well visible as a dark dot, so we can measure distances between the atoms, see the outline of the fullerene itself. It's even easier to see krypton in the STEM images, so it's much darker spot, and of course, it's harder to see carbon atoms in its background. What also can be done, we can use electron energy loss spectroscopy and produce a spectral map of the krypton atoms in a nanotube. Or we can overlap spectral map of the carbon, red, with a spectral map of the krypton, blue here. And you can see side walls of the nanotube as red, and the krypton atoms as blue in the middle. So this is all very nice. So let's just remember that electron actually excites molecules, it excites bonds. And 80 keV is not enough to break the bond in the carbon nanotube, but it is enough to break bond in the fullerene. And as we do so, the fullerenes merge together within the nanotube. So here is a movie. So you can see the fullerenes, they start forming defects, and then they merge into the chain of the molecules. What that means is that we are releasing these krypton atoms out of the fullerene cages and allowing them to interact with each other. So, so if you look here at the still images from the movie I just showed you, so this is one of the early stages of the merging of the two C60 cages, which still has a bottleneck, which is too narrow to allow for the two krypton atoms to meet each other. And then in this image here, the bottleneck has been annealed, it's disappeared, and the krypton atoms are allowed to meet and touch, and they form van der Waals dimer. So we know that by measuring distance between the krypton atoms and comparing that to the van der Waals diameter of the atom. So this is very exciting because van der Waals dimers, they are quite transient species, and they of course exist, but they're very difficult to detect. But here we image them in direct space, just in real time, using this confinement effect. What also happens with these dimers that occasionally become ionized on very rare occasion, and then the bond between the krypton atoms become covalent, so atoms move closer to each other. But this is transient situation because they regain the electron very quickly and go back to the van der Waals dimer. And we can correlate this distance between the krypton atoms with the bottleneck that develops between the fullerene cages. So it works very well. What also is very interesting in the system is that if we allow enough time for the fullerenes inside completely anneal, what will happen then is that we form internal nanotube within the original nanotube. So it's a double wall nanotube now. So on the first top micrograph, you can see the still bottlenecks between the fullerenes. So krypton atoms are immobilized. They're sitting pretty much where they were inside the endohedral fullerenes. The second image, it's already well annealed tube in the middle, but not so much at the ends. And you can see some krypton atoms and some are already delocalized. And the final image is where the tube is completely annealed, so the krypton atoms are free to move in one dimension within the nanotube. So how do we know that krypton is still there? Because we don't really see it in high-resolution TM. Well, we know from EDX, energy dispersed X-ray spectroscopy. So we start with 0.4 atomic percent of krypton in our material, and the same amount remains after the annealing of the fullerenes into the tube. So it's somewhere there. We simply don't see it in images. Also, X-ray photoelectron spectroscopy confirms that the krypton is there, and the chemical state of the krypton inside the annealed tube is closer to the gas state than to the single atom state as it was inside the fullerenes. But perhaps the strongest evidence comes from the EELS spectral mapping. So here we are mapping the M45 EELS edge of krypton, shown in blue, and red is the pi star edge of the carbon. And here krypton manifests itself very clearly, much more clearly than in the bright field images. So it's there and it's delocalized and it's moving around. So this is very strange state of matter, one-dimensional gas. So this is where the atoms cannot really pass each other as they move in the nanotube. They have just 1 degree of translation freedom. And that's the state where the atoms stop behaving like normal atoms. They're not governed by the Boltzmann thermodynamic anymore. They behave more like a species obeying the Pauli exclusion principle, which means that our atoms start behaving like fermions rather than bosons. So it's quite a weird stuff, and it's been predicted for a few years ago. And it's quite exciting actually to have this material now in a solid state in our lab. So this works. The same works for argon. So we're going up in the group of noble elements. So this is argon in fullerene. So we also can merge fullerene cages by electron beam. And we can do the same with neon. So I don't have it in my presentation, but we have very similar data for neon. Not sure what we can do for helium, but it's definitely up to the neon it works. And here is the van der Waals pair of the argon atoms, just in the same way as we had it for krypton. It works. So let me also say a few words about molecules, very small molecules that can be squeezed into the fullerene by molecular surgery method. So it's HF and H2O. So here, imaging microscopy images are a little bit more difficult to interpret, and I don't have time to explain it in detail why, but only in some of the fullerenes we see contrast corresponding to the position of fluorine or oxygen atom. So you can see here at the bottom is the intensity profile, which is taken down. For example, 1 is the red line here. So across the fullerene cage, and you can see the dip in intensity in the middle, in this particular case corresponding to fluorine, but it's not so clear in the molecule next door. So it's to do with the rotation of the fullerene in the nanotube, and it really depends whether the carbon atoms on top and the bottom projection of the fullerene overlap with the atom of fluorine in the middle. Only under these conditions we get sufficient single atom contrast. What is very important here is just one thing to draw to your attention. This work was done at 30 kilo electron volt. So this is something called Zalve microscope in University able to do. And this is very important because at 30 keV, the energy transfer to carbon is can be up to 5.6 eV. So this is not enough to remove carbon atom from the nanotube and even from the fullerene. So that's to protect our sample from degradation in electron beam. The maximum transferred energy to the hydrogen atom is 67.8 eV at this energy, which is still very high. And what happens is that we break the hydrogen fluorine or hydrogen oxygen bond in H2O quite quickly under these conditions. And to surprise of many physicists who work with me, it was not heterolytic dissociation of the bond, so where we form proton and the fluorine radical, fluorine anion, but it's a homolytic process where we form radical of the hydrogen and radical of fluorine. So, and it's quite surprising, but it is true, and it makes sense because this is done in water. HF would dissociate as an acid to produce a proton, but because we work in vacuum effectively, the more energetically favorable process is homolytic bond dissociation. So in all, we end up with a hydrogen atom, which can permeate through the fluorine cage and can escape either through pentagon or hexagon under our imaging conditions, leaving behind atom of fluorine sitting in the middle of the cage. So, so what is evidence? What evidence we have? Again, EELS is very helpful here. So at a SuperSTEM facility directed by Quentin Ramas in Dasbury in the UK. So we EELS can go to vibrational range to very low energies. And in vibration range, we clearly see this strong band corresponding to the HF bond vibration, which after exposure to the electron beam decreases and then disappears more or less. So that is interesting because effectively we are creating free radical oxygen and free radical fluorine in C60 cage, which is quite exciting for many reasons. If I show you the movie of these molecules, you notice that actually things are not quite as we should be expecting, because the fluorines don't stay intact as they should be at 30 keV. They do break up and they form this peanut-looking structures, just like I showed you with in the case of at 80 keV. So that should not really happen, and it does not happen with empty fluorine at 30 keV. So something else must be happening here. Let me tell you what is happening. So we need to consider what is the fate of this hydrogen atom, which escaped the fluorine cage. It's a very fast hydrogen atom, which is still trapped in the nanotube. This hydrogen atom can pass the kinetic energy, the momentum, to the atom next door, such as carbon atom. So we are now talking not about direct energy transfer from the electron beam to the atom of carbon, but we're talking about the energy transfer through hydrogen atom to the carbon atom. So we need to modify our equation, and what we need to know is the mass of the hydrogen, mass of the carbon, so X is the carbon atom, and recalculate our maximum transferred energy, and that the numbers that we get. So if we look at 30 keV electron beam, the maximum transferred energy to carbon direct from the electron beam is 5.6 CV, but through hydrogen atom is 18.9. So what that means that we increase significantly the amount transferred by hydrogen, and this is of course bad news for the carbon atoms of the fluorine, and that's what causes their break up under these conditions. Again, hydrogen is really challenging in TEM, and if possible, we should not really look at the molecules containing hydrogen at the single molecule level, because it complicates everything. But again, if you just forget about this hydrogen effect and just focus on what is left on inside the fluorine, just to want to emphasize what we're left with is a neutral atom of fluorine and neutral atom of oxygen. These seem to be quite stable structures on their own. So these are calculations which are showing that it takes nearly 9 eV to expel fluorine atom from the fluorine cage, and 4 eV for the oxygen atom to come out. So what that means that these molecules can be quite stable, and we can use them for things such as quantum computing or quantum clock. And based on this little discovery, we started a new project called Taming Radicals, funded by the Liverhome Trust. What about metals? So I said that actually it is possible to entrap metal atoms in the fluorines. So that is done by the electric arc discharge using graphite as a source of carbon with some metal salt. And this is one of the early molecules that I studied by electron microscopy. This is dysprosium, which is one of the lanthanides, again, nice and heavy, so we can see single atom contrast. And this is C82 cage rather than C60. Metal atoms sit off the center of the fluorine cage. That is different to krypton. That is because the interaction between the cage and the atom of the metal is ionic. So metal is in cation form, and the fluorine cage is negatively charged. So effectively it's a salt. With metal atoms, things are also quite interesting, and we can do similar things as we did with the krypton. We can release the atoms from the fullerene cages. We can make pairs of atoms of metal. But of course, what happens is that these metal atoms are also quite active towards the nanotube. And what you see here is the cluster of about 10 atoms break the nanotube during our observation. So our test tube has failed. So one has to be very careful by choosing metals. And I have an entirely new story about the metals that is actually allows us to study some processes related to catalysis under electron beam. But this is a story for another day. So let's return to molecules, and this is my final example. So is there something more complex we can study? How big we can go, when we talk about reactions in carbon nanotubes? We like this polyaromatic molecules, and this one is called poronin. It consists of 24 carbon atoms and 12 hydrogen atoms. Hydrogen is bad news. So just to remind you, at 80 keV, we have 188 eV energy transfer to the hydrogen. So it's quite difficult to study this molecule. We did try. We did try to replace hydrogen for deuterium, which of course doubles the atomic mass of the hydrogen atom, and it essentially halves the energy transferred from the electron beam, makes this molecule to survive longer in electron beam, which is fine, but not long enough. The best thing, of course, to get rid of hydrogen completely and replace it with chlorine. And chlorine is much heavier element, and therefore the molecule, which is called perchlorinated coronin, PCC, lasts in electron beam much longer, and we can study dynamics of this molecule. We started with PCC on graphene, where the carbon-chlorine bond can be broken up, and we just release CO2, chlorine, forming this biradical on the edge of the molecule, which then bonds to the graphene layer. What we see in microscope, we can see this circular outline of the molecule when it lies down, and then when it stands up, it becomes a line. So now we look at edge-on this molecule. So definitely reaction works. The most interesting thing happens inside carbon nanotube. So we can pack this perchlorocoronin molecules inside the nanotube like you would put Pringles crisps in the tube. So in fact, I think it's a very good comparison, because the PCC is not completely flat. It's slightly warped, just like Pringle crisp. Or chips, I think. I must say chips, probably. So it's a pack of the disc-like molecules in the nanotube. They come out very well in TEM. And now we can watch this reaction step by step. So watch this moving at the bottom of the slide. So you can see that this stack of molecules transforming under electron beam, and we're forming something that looks like a ribbon at the end of this process. So in fact, what we formed here is a graphene nanoribbon terminated with a zigzag edge and decorated with the chlorine atoms around the edge. I must say that this is first time when not only we are looking at the process or reaction or chemical bond, which is already known before we started doing microscopy. This is the first example of the chemical reaction discovered by the electron microscopy. So, and actually it's a very important product. Graphene nanoribbons are very useful and popular nowadays. And we discovered this reaction under the electron microscope, and we understood exactly now this reaction mechanism. So including key intermediates, and we even know the barriers for the key stages. And we've done a little bit more work since then, looking at the determining the reaction rate constant and the cross sections of this reaction directly from electron microscopy images. So this, I think, shows how far we can push chemistry in the electron beam. And I just want to finish my presentation by the quote from Schrödinger, who said that we cannot make any factual statement about a given physical object without getting in touch with it. This touch is a real physical interaction. The object is interfered with by observing it. So, of course, that creates a headache sometimes if you want to study object in its pristine, intact form, but also it gives us an opportunity to use electron beam not only as an imaging tool, but also as a stimulus for chemical reactions at the same time. So I would like to thank everybody who worked with me on this project, all members of my research group here at Nottingham, my collaborators in the Zalva project at the University of Ulm, Ute Kaiser and her team, Richard Whitby, who provided many of these endohedral fullerenes, Quentin Ramas, SuperSTEM facility, and colleagues in the School of Chemistry, Jesem, Emerson, Elena, and Sadek, who work with me on this project. All the funders, University of Nottingham, the EPSSC, that's the main funder who provide money for research in physical sciences, and the Royal Society. And thank you for your attention.
Wow. Thank you very much, Andrei. Brilliant stuff. Just to connect while we're waiting for any questions on the chat or on the Q&A, please, is to put it in context with the biology people. What sort of electron doses are you using here? Because they're typically in the electrons per square angstrom type of dose or dose rates per second. Yours are much higher.
Mine are much higher, yes. So the dose rate, everything what I showed you today is in region of 10 to the 6 electrons per square nanometer per second.
10 to the 6 electrons per square nanometer.
Per second. Yeah, per second.
Yeah.
So this is a high Bob, and this, I think this is the future really. So if we can push it to low dose, using the same methodologies but going to the low doses, then we may be able to study more fragile, more delicate molecules and really open up opportunities for organic chemistry in TM.
Right. Would you propose to do that within carbon nanotubes, or would you use graphene as your substrate, or maybe have one graphene layer and put another one on top with the molecule in between? How would you do this?
That's a good question. So nanotube is good because nanotube is a molecule is confined there, so it cannot diffuse too far away, and it just stays still where you want it to be. The problem with nanotube, of course, there's a limited size, so we cannot put really large molecules in nanotubes. But then, of course, one can synthesize bigger nanotubes. Graphene is good, so we do use graphene occasionally. The problem with graphene is contamination. So as you know, there is no such thing as clean graphene. There is always something adsorbed on it, adventitious carbon, whatever comes from the microscope. So it's more open system compared to nanotube, and therefore it has challenges of its own. I think if our community can learn to use graphene bilayer and clean graphene, so there is no anything else in it, and try to sandwich molecules of interest between the two layers of graphene, I think that would be probably optimum conditions, because you get all the benefits of the carbon nanotube. Have a sealed system, if you like, but without difficulties of contamination. Yeah.
Right. David DeRosier had a question here sent through chat. I don't know, David, if you would like to answer it in person, ask it in person.
Yes, that would be fine. My question is, seems to me amazing that the rates at which those processes you're looking at are slow enough that they can be captured in electron microscope images. And I'm wondering, did you arrange that to be so, or it just seems to me, I always think of, reactions of that kind as being in, way some millisecond or even faster. So it seems to me kind of surprising that you can get those gorgeous images of changes.
David, very good question. So of course, we choose deliberately heavy elements. So my first example is rhenium. So it's a very heavy element. So it's has a low amount of energy transferred from the electron beam. So that's already good. It slows down the process. But the other thing, of course, is that we can slow down our reactions by simply spreading the electron beam. So there's a direct relationship between the rate of the reaction, how fast the atoms move or bond breaks, and the brightness of the electron beam that we use. So this is our major tool, I think. And we can, yeah, sometimes it's very frustrating. I see something very fast, I cannot capture it. But in some of the cases, of course, I showed you only successful examples. There are hundreds of experiments which failed. But yeah, so this is, you're absolutely right. We have to choose the right system.
And so can temperature be used as a variable? Could you heat and cool?
Temperature plays no role in these reactions, Bob. So because these are electron beam activated reactions, and we did try to do some cryo work in nanotubes. The rates of the reactions don't really change because the energy transferred from electron beam completely overrides the thermal excitation of the molecules.
So as you know, with our in situ work, we try our darndest to reduce the electron beam effects to zero if possible, but as low as possible. And you're doing the opposite. And so we have found in the past some benefits from the electron beam, particularly in some ionization reactions, can be similar to what happens in an electrochemical cell, for instance, where you might have protons moving around. So there are some circumstances in which I am convinced that the electron beam can help, and your work is going some way to convincing me that you can use it in other ways also.
Fantastic. That's great. So that's exactly the message of my talk. So beam damage can be useful if we understand what is happening there. So it can be useful. It can help to understand chemistry and physics of our systems.
Good.
So-
And there's a question on the Q&A. Would you?
Yeah,
Can you open
I
this?
can see that. Yeah. So Michael is asking, is the first break in the walls of the nanotube a bond formed with it, or just the atom breaking the wall kinetically? Right. Very good question, Michael. Very insightful. So this example where the nanotube wall breaks, that was with dysprosium, and normally what happens with metals. So metals seem to be able to break the bond. And this is not the metal itself that breaks the bond. Of course, it's the electron beam, because that's the source of energy. So, but the metal is a catalyst. So what metal does, it activates the bond. So in your terms, you're right. So essentially, the metal atom binds to the carbon atom of the wall of the nanotube from inside, and then the electron beam transfers energy to that carbon atom, which already has weak bonds with the rest of the carbon framework, and the defect is formed. So that's what I said. This is basically what it tells us. It's something to do with about the catalysis, the way how the metal atoms activate bonding between the carbon atoms. And I have a separate project on that where we actually learn a lot of catalytic information from the beam damage in the presence of metals.
I'm wondering if Wa has any comments and applications for his field.
Not off top of my head. I need to digest a bit in the details. How the samples are prepared, because we do everything at low temp in a vitrifying sample. And as Andrei points out, he did some low temperature experiments with your samples. What did you see? You have been able to see the same phenomenon faster?
Exactly. Yeah, exactly the same phenomenon. So and which tells me essentially that the reaction is activated by electron beam. So temperature is kind of irrelevant. But what actually sometimes we see, sometimes our products are gas molecules, such as in the last example where I showed you dechlorination of the PCC. Then it's chlorine is the product there. So in the cryo-TEM, we could see the crystal of chlorine growing outside of the nanotube, which basically backed up our mechanism of the reaction. So that was very interesting. One thing I always think about vitrified samples, then of course everything is in water. So you have H2O surrounding your molecule of interest, and in terms of the beam damage, it's the damage on the water molecule, I think, could be quite significant. And this very fast hydrogen atoms, which I mentioned, they may actually create secondary damage. So one of the things I think maybe I'm wrong because I'm not really in your area, but I noticed that some colleagues started using deuterated water instead of normal water for vitrified samples in sort of attempt to stabilize the beam damage. Is this so? Or?
Well, I would tend to think they are about the same.
Yeah.
Between the X2O and D2O in terms of the damage. Because once the bonds is broken and things move around. And
yeah.
So in the sample you did you get your nanotube completely hydrated?
So we've done 2 experiments with where we had hydrogenated coronium just with normal isotope protium and the deuterated coronium. And we found out that the deuterated version was stable, I think, longer by a factor of 2.6. So you know, it was lasting longer in electron beam because of deuterium. And that is down to the fact that deuterium has double atomic weight of the normal hydrogen. So it receives less of the kinetic energy from electron beam. And that means that the bond is more protected from knock-on damage.
I see, because you are, so your damage, what's the damage mechanism? Is it knock-on damage or it's a radiolytic damage?
It's knock-on.
Knock-on, okay.
Yeah.
So the way I understand in the damage in organic sample, we are dealing with the radiolytic damage once the chemical bonds is broken and then things start moving around.
Okay, so it's a different. I think you're right. In thick samples, if it's a thick organic crystal, or I don't know whatever thickness of ice one needs to have radiolysis. So I think radiolysis may take, because also it's insulator your sample, I guess. So it's quite difficult to dissipate charge once start charging.
And I presume that you have not looked at any radioactive atoms in your carbon nanotubes.
That is my dream, actually, to have something radioactive with a lifetime short enough so I can see the radioactive decay at the atomic level. That would be real fun.
That would be real fun indeed. Yes, the splitting rather than the fission.
Exactly. Yeah.
Fusion rather than the fission would be completely different. Good. Well, with that, let's close on that note. So, Wad, do you have any messages for our guests?
David, do you have any last word advice?
Yeah, I think when I talked about some of my fanciful ideas is that physics says any of those things I've suggested is possible. It's a question of doing the engineering to get it to work. So it's a question from the community, how much do you want a freeze now push button, for instance? If it's really important, I'm sure it's doable. And so I think that's the message. There seemed to be a lot of enthusiasm for it at a recent meeting. I don't know the answer.
Okay, so what you're saying is all these theoretical ideas need to put in practice. And so you either build a new gadget or develop a new algorithms. It's all within the bounds of physics. So that's what you're telling us. Okay, we will keep that in mind. And for those who are in the audience, just go to do it.
Yeah.
Okay.
Well, all right. Well, I'd like to also thank David and, of course, Andrei for these fascinating talks to show us the power of electron microscopy. And I'm looking forward to seeing you realize your dream, Andrei, and to see the atoms break apart or whatever they might do in the radioactive state. And so really good luck with that. So thank you both for fantastic talks from WA organization. Yi, of course, and Jane for setting this all up and guiding us through it. And so thank you everyone for attending, and we'll see you in a couple of months' time. Thanks.